Hi guys, so today we're going to go over a couple of different topics. So first we're going to go over SQL logic and some SQL tables and how to some common SQL clauses and what those mean. So first we will go over some common clauses. So first we have the select statement. So the select statement gets the names of the fields that we want. Sometimes we also use aliases or which refer to the names of the tables that we can use. So for example, for in this select clause, we're using C dot customer ID, C dot first name, C dot last name. That refers to the customer C table, and the C is the alias that we're referring to the customer table by. And so when we have these select statements, we can use C dot or the alias dot something, and that allows us to be more specific when we're doing our select statement, we're able to select the appropriate columns. Then we have our joins. So there's typically three types of joins. So we have inner join, left join, and outer join. There's also a right join, but every right join can be replaced with a left join. So typically we have inner join, and what inner join does is it's going to get the matching rows between the left table and the right table. What left join does, it's going to get all of the records of the left table that match with the right table. So and it's going to get all the records from the left table. So even if there are records from the left table that don't have a match to the right table, it will still return those records. And for the right table records fields, it will have them as no values. So all of the records that are in the left table will be present when we do a left join, and similarly for a right join as well. And outer join, you can think of them as a combination of both inner join and left and right join. And so here we have our select statements. From is the table that we're getting this from. We have our join, which refers to like how we're combining these data frames, these tables or these two tables, and then group by is when we are aggregating by the specific fields in our data set. So in this table, we're grouping by customer ID, first name, last name. So customer ID, first name, last name of this group by data frame will all be unique. They're going to be unique combinations. And how are we aggregating them? It's by the sum of O dot amount. So what this is going to look like is we have our inner join. We have our inner join. It's going to get the key that here is the primary key and the foreign key. So the primary key is the unique identifier in a table. The foreign key establishes the relationship to another table. So it refers to how can we link, what column can we use to link to the primary key from another table. And so it establishes the relationship. That's what the foreign key does. And that's how we're able to do the join. And then, as we mentioned, the group by, these combinations will be unique. And we are grouping by what's the operation that we're doing? We're doing the sum of O dot amount. So when we do this initial join here, we're going to have this one twice actually, right? Because there's two ones in the orders table. We're going to have a two. We're going to have one, two. We're going to have a three, one, three, and then four, five as well. Okay, so one of the things that you'll notice here is that, yeah, we had one customer ID equals one in the customers table, but we had two of those customer IDs in the orders table. When we do an inner join, both of these will get aggregated and will be returned. So that's one thing to note. And let's see, go over this. And then how we are grouping this by, we're grouping this by the sum of O dot amount. And so this amount refers to the orders table. We're going to be grouping by customer ID, first name, last name from our join. And then we're going to be taking the sum of O dot amount. That will be referred to as total spent. And we are filtering. Having clause is what we use when we want to filter after we've done the aggregated step. And this is similar to where, except that where we do it before we have aggregated the data frame, having is typically used after like a group by when we have already aggregated the data frame and we want to filter based off of some aggregated function. So in this case, we want to filter based off of the sum of O.amount. So that's an aggregated function. We want to filter it. That's why we're using the having clause instead of where. We can use this before we've even aggregated the data. We can use where. But after we've aggregated, we typically use having. And then order by, again, pretty standard. We're ordering the table in descending or ascending order based off of a certain column. In this case, it's the total spent or what the group by aggregation is. And then here we can also have a subquery. So this subquery returns a table, and this table is now used in a different query. So it's like a nested query. It's a subquery. This query returns a table, um, or like a column, and then that's used as a part of a larger query itself. So that's another thing that you can do. It really allows for more flexibility, merging different data frames or merging different tables, and really just offers more freedom and flexibility in writing your queries. And then let's go move on to left. So we talked about left join, right? Left join, we're going to include all of the values in the left data frame, left table that match with the values in the right table, even if there are records in the left table that don't have an ID or don't have a link to the left or don't have a matching ID to the right table, we will still include those records with having the null values as the values for the columns in the right table. So that's another thing to keep in mind. Now let's move on to a LeetCode question. So longest common prefix. The question here is we are given an array or a list of words, and we want to find what's the longest common prefix. So prefix obviously is the beginning of a word, which is the prefix. What's the longest prefix that's in all of these words? So in this case, we have flower, flow, flight. F is right a prefix that's in all of these words, but FL is the longest prefix that is in all of these words. So how can we develop an algorithm that's able to get this longest prefix? Well, there's many different approaches to this. You can take this two ways. You can start from building up your prefix from starting with nothing, or you can start with already having a predefined prefix that you're using. So if you start from scratch, if you start from an empty string and you're trying to build up your prefix, what that would require you doing is it would require you, so let's say we have F, right? We know that F is in all of these, uh, is in all of these elements. And you would set the prefix to be the first element of the first character of the first element in your list. And then you would check if all of the other elements in the list also have that element. If they do, then you go add another letter, another character from the first word to your prefix, and then you check if the other elements also have that prefix, and you keep on going until you get to a point where that prefix does not exist in the other words or or uh, you can also do this. You can also start with the largest word, and so that will make it easier. So you only have to do this once. Don't have to worry about, oh, what if it's actually the shortest or the longest? It could be more. So you could actually just start with the shortest one, and that would work. Okay, so that's like one way. Is like you build this from the ground up. You build this from scratch. The optimal solution, or not the optimal, but one of the ways, one of the more common ways to do this is you start with the prefix being the first element. So in this case, our prefix is flower. It's the first element in STRS. And then we're looping through this entire array. And then we're seeing as long as we are not able to find this prefix in this word, we're going to iteratively remove the last character of that word or of the prefix. We're going to remove the last character of the prefix such that that prefix is present in the word. And we're going to do this for all of the words. So what did this do? Let's go step by step. So initially, our prefix is going to be flower. And then we're going to loop through the rest of the string or rest of the list. And flower, do we see flower in flow? No. So then we take out R. Do we see FLOWE in flow? No, we don't. We're going to take out the E. Do we see flow in flow? We do see flow in flow. So now we go so then this while loop is going to break, and then we're going to go to the next element. So we're at flight. Now, do we see flow in flight? No, we don't. Do we see FLO in flight? No, we don't. Do we see FL in flight? We do see FL in flight. And so that's going to be the end of our loop through the list, and that's going to be what we return. And so let's see what are some of the common patterns and things that we can learn from this. So the first is the usage of a while statement. When we're doing a lot of these problems, it's very easy to just use for loops, but really having an understanding of while loops and when to use them and actually even implementing them and using them is very useful. And is something that I feel like we make sure that we're aware of. And that's a normal part of our thought process using while, because I feel like a lot of times like we just have for loops and then we're all always just using for loops, but while loops actually are able to solve like a completely new dimension of problems. And so where there's like no new stopping criterion where you want to iterate over like a certain like for a certain condition, but you don't have like a stopping criterion. And then two is you start with the full answer. So as I was saying, describing in the beginning, you can start with like a blank prefix, like with an empty prefix, and then you can build it up. Another way is to go backwards, where you start with the full entire like default answer of the prefix, and then you sort of iteratively update your prefix such that it's able to get to the correct answer. And so you can start with the full answer, and it's also like a going backwards type approach. So you can use that as well. So starting with the full answer and then going backwards is another technique. The third is the absoluteness of each element sort of sufficing. What I sort of mean by this is the fact that because we're able to see in flower which prefix in would fit in flower, now that serves as the basis point when we go to flow. And then when we reduce it to flow, that serves as the basis point for when we go to flight, the prefix. So because of that, we're able to sort of maximize what our prefix like could be at each iteration. And so that was like another like paradigm or perspective that we can get from this problem. The fourth is the constant updating of the answer. So this goes back to when we first initially start with the full answer, we also have to update it depending on like a certain condition, depending on the condition that we meet. In this case, we update the prefix when we see that the prefix is actually not in the list of strings. And when we see that the prefix is not in the list of strings, we remove the last character of the prefix such that it then becomes in the that then it is present in the string itself. So that's longest common prefix. It's a very simple problem, but there's many things we can learn from this, and that's one of the ideas I really want to bring forward here. Is that yeah, these leak code problems, some of them are leak code easy, but even from leak code easy problems, like the way of thinking and the patterns and the techniques that you're using, you can extract a lot from those that you can apply to future problems. So this is the really deeper dive into the nuances of the problem that you really want to focus on. It's like, what was the thought process? What are some of the ways that I could have done this a bit differently? What tactics or techniques did I use that helped me solve this problem? What can I learn from this problem? Really thinking critically about the problem and how you got it, how you solved it, even after solving the problem. That's going to help you solve future problems as well. Now let's talk about just EDA and data science. And when we do a data science, when we are given like a data set from like a client or from a company or from a business problem that we're working on, really like we want to get an understanding of the data. Like what is it about the data set that intrigues us? What is it about the data set that we should know based off of the business context? Like what's the story around this data? Like how is this collected? What's the target of this data? What's the purpose of this data? Who is this data given us to us by? Who was it collected by? How was it collected by? What do the columns actually mean? What range? What do you expect these different columns to actually fall in? Is there any missing data? Really getting an understanding of the data will also even help you detect anomalies, which is like sort of the second point is, are there any missing values in the data? Are there outliers? How can we detect that something is not looking right in the data? The only way we can do that is we have an understanding of the business problem, and we can then uh, from the business problem we can see if our data properly aligns with that, and we can sort of develop a story regarding the fields that we see in the data itself. So really good getting a nuanced, complete understanding of what the data is, so that you're able to really understand the analysis that you do on the data. And then like some other things, like obviously EDA, we want to do distributions of like numerical variables. We want to draw box plots. We want to get an idea of what the data is. We want to do value counts in a very visual format. And one of the things I would recommend here is really just creating like a bunch of plots and putting them like in one cell, like a bunch of common plots, putting them in one cell. Because like if you just keep on making plots, going to add a lot of unnecessary complexity, and just having like one cell with all of the common types of plots will make it a lot easier to read, and it's really going to normalize a lot of the EDA complexity that we perceive. And then just doing a multiple group by. So what this allows us to do is it allows us to view the data set in segments, group them by into segments, and seeing like which segments are performing better depending on the problem, but really doing a bunch of group bys. Also doing a lot of pivots as well. So this is something that you can use where you can actually put the data into Excel. There are certain functions in Excel that you can use, such as pivot tables, that actually may get you like it's very a better understanding and visualization of the data. And it's something that the group buys are actually a lot easier to do and a lot better in terms of visualization than like a group buy in Python. And so you really want to take advantages of like certain softwares might be good at doing certain things, and taking advantage of like all of those opportunities and software packages to really get a nuanced understanding of data. That's very critical when you're given a data set and a business problem. Centralized limit theorem states that as the number of random variables increases, and as we're taking the sum of these random variables, regardless of what distribution they even come from. Random variable one could come from gamma. Random variable two could come from Pareto. Regardless of whatever distribution that these random variables come from, when we sum them or when we take the average of them, that will follow a normal distribution as the number of these random variables increases. So that's what the central limit theorem says, is that as the number of random samples that you take, regardless of the distribution, the more random samples you take, the mean of those random samples or the sum of those random samples will approach this normal distribution. So that's what the central limit theorem states. Very, very fundamental theorem in statistics and the basis behind hypothesis testing, confidence intervals. And so this is something that we really want to develop a nuanced understanding of. So, like as an example, if we take a large number of random samples from any distribution, they will tend to approximate normal as the sample size increases. Another example is if you have 1,000 students' test scores, that are all skewed, so they don't follow a normal distribution, and you repeatedly take 30 random samples of 30 students many times, the distribution, the sample mean, will approximate normal distribution. So that's something that we discussed before about the summation or the average of random variables following a normal distribution. Now let's get into some t-tests or z-tests. So one sample t-test refers to when we have like a mean of a sample. So we have these different data points that are a sample. We take the mean of them, and we want to compare them to like a population mean or to a different value. And so we want to see, does this sample that we have, is it significantly different from like the population mean or from another mean that we're thinking about? So an example is, does the average weight of a sample of 20 apples differ from like 200 grams, which is like which could be like probably like the number that you're given, the population mean, And so if we want to compare like the mean of a sample to like another value, we would use one sample t-test. Two sample t-test is what we would use when we have two different independent groups. So we want to compare how different are these two independent groups. So if we have, for example, like the test scores between two different classrooms. These are two different groups. We want to compare the difference in test scores between these two different groups. Are they significant or not? Is there statistically significant difference between the test scores between these two classrooms? Or obviously they're going to be like slightly different, but or is that difference more due to chance and it's reasonable that sort of they have similar means? And we want to use a z-test when the population standard deviation is unknown. This is very unlikely to be the case. So it's very common practice to actually use t-test as well. And one of the assumptions of both t-test and z-test is that the data is normally distributed. There's other tests like Kruskal-Wallis and Mann-Whitney-U that doesn't require the data to be normally distributed, but for z-test, t-test, we typically require that the data is normally distributed. Now, if the population is normally distributed, even if though we have a small sample size, we can still use the z-test. So there are some like of these nuances and cases where we could use z-test. Chi-square test of independence is when we have two categorical variables and we want to see whether one variable is actually independent from the another variable. So if we have two variables, gender, male, female, and then smoking status, smoker or non-smoker, if we want to see if gender is independent of smoking, non-smoking, or if like being male or female increases the likelihood of smoking or not, if we want to understand that, we would have to use chi-square test of independence. And typically this is when we have large sample sizes. So there's a rule that we need to follow when if the expected value in these cells is has to be greater than 5. And so that's when this would be valid. And also the observations have to be independent. Now let's talk about Git. So you can think about Git as a version, like Git is a version control system when collaborators on a project want to make different changes, they want to have different versions, and they want to collaborate on a single project. We use Git, and so Git we have our master branch, which is like the main code base. Then we can fork the master. We can fork the master branch, which is creating a personal copy of someone else's repo or another repo. And that creates our own version. That creates our own remote repository that is stored on the internet, whether it's on GitHub or GitLab or Bitbucket. It's a remote repository that's on the internet, but that you can think of that as like our own version of the repository. Then we can, so you can think of this as like, and then we can uh, clone that remote repository onto our local. And so we have our local repository as well. We make changes there. When we're done with like a change there, when we make a branch for a feature, we can push that change to our remote branch and the remote or to our remote repository. Or remote repository will then contain those changes. And then if we're ready, we can submit a PR in which the owner of the branch of the master will review the PR and see if it's okay to merge. If it is okay to merge, then they will merge it into the central code base. But this is a diagram of how it generally works, like the fork from remote repository to master branch. That's how PR is made. We do push pull. Pull is getting changes from the remote, which will be updated with the changes with the master branch. Pulling changes from the remote down to your local repository so that you're able to make the changes uh, alongside like the other updated changes that are also happening. And then typically a feature is only one branch. Branches can exist both locally and on the remote repository as well. And then an analogy is that of a book. So sometimes uh, these analogies are very helpful when you're trying to understand these different concepts. So you fork a book from another author to start working on your own version. So this is when you create the fork you're creating your own version on the internet. You write a new chapter in your branch. So this is when you write new code on in your local branch that you have. You make these adjustments. Then you push your chapter to the remote bookshelf or to the remote repository. Right. So this is you finish making the changes. Now you're adding the chapter that you've written to this bookshelf. And now we create a pull request to have the owner of the main book see if the version of the book that you're working on or the book now on the remote bookshelf is worth adding into the central code base or into the master chapter or the final version of the book. If they review it, and if they review it, then whatever was on the bookshelf or was on the remote repository will get merged into the central code base or to the central chapter. So this is an analogy. This book analogy is something that you can use to really get an understanding of what this Git 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 repository and this Git workflow entails. And a couple other things with normalization of systematic advantages refers to the fact that when we have these different systems that we are implementing on our lives, whether it's a new paradigm, whether it's a new thought pattern, normalizing it is going to help you gain more comfort in it. It's going to help you have more fun in it. That's one thing. Two is resolving internal cognitive battles through math and programming questions. So thinking of psychological tendencies, understanding the nature of other people, understanding the nature of your mind, understanding the nature of how these different things work as like a math or a programming question. You're trying to solve the problem. And then analogies and examples are the best way to learn because they integrate existing information that we have in our minds to new information. That's one of the best ways that we can actually learn is when we're able to integrate new information that we get with prior information that we already know. Gamification, treating everything as a game, is another tactic, and then every opportunity is a you can see that as a challenge slash the improvement and growing of skills as well. Picks for week 10, obviously Jets money line at the Cardinals. One of the reasons for this is Jets just broke like a 6 game winning streak. I think they win consecutive games. Two is Cardinals have already done an upset at 305, 325 as well. And then Eagles money line at Cowboys. This is due to the fact that the Cowboys have already upset the Browns during this time, as they'll also upset in prime time as well. So Eagles money line, Jets money line, two official picks for NFL Week 10. You can think of cloud services as like city infrastructure or resources. So in the same way that the city has electricity, the city has water supply, the city has a road system that the civilians, that the people can use, in the same way cloud platforms, AWS, GCP has to have different services. In the same way electricity, roads, water supply have different services that others can use. So S3 buckets, GCP, Google Cloud Storage, or like compute engines, you can think of them as like the electricity or the roads that people can use to like deploy their applications. So you don't need to build your own road network. You don't need to build your own power plant. You can use the services given to us by the city. You can use the services given to us by AWS or GCP. So in the same way that cities offer these public infrastructure services, cloud platforms, AWS, GCP, Azure allow us to better to use these services to attain the project goals that we have. So that's it, and I'll see you in the next video. Thanks.